coming in add to the same side. In the end, we'll have cis stereochemistry. Here's another reaction that involves cis stereochemistry. It's called reduction. Sometimes it's called hydrogenation of alkenes. It's already naturally in our notes lumped together with another syn addition reaction giving cis stereochemistry. It's also sometimes referred to as catalytic hydrogenation. And it's just adding hydrogen across an alkene. You can take hydrogen gas, and it requires the presence of a special catalyst, let's say palladium metal, deposited on carbon. Palladium metal is quite expensive, and solid metals aren't very reactive. But if you make a thin film of palladium onto graphite, it's this fine black powder with a tiny amount of palladium. It has a special effect with alkenes in the presence of hydrogen gas. It has the effect of adding two hydrogens on the same side, and this is the result of a syn addition product, where both reagents or reactants, atoms, can only be deposited from one face of the molecule. They can't come one on the top, one on the bottom. They can't be mixed up like a carbocation. They both come in at the same time. I'm going to show how this particular process works for alkenes, but this knowledge below here is not required. Never going to ask anyone this, but I want to show us why it's a syn addition product. In essence, when you take hydrogen gas and palladium on carbon, other metals can do this. We're just going to draw like a particle of carbon, like graphite. And on this is deposited palladium or platinum metal. I use palladium this semester. Little tiny bits of this deposited everywhere. And when you put hydrogen gas over this particular surface, hydrogen actually attaches to the palladium. A very, very complex process. And it's just sitting there waiting. What it's waiting for is an alkene to come floating by. And alkene floats by. And I'm going to draw the mechanism, but you're not required for this one, okay? Not required. Put in big letters in your notes. Don't ask me if it's required. It's not required. Students every semester ask me this stuff all the time, and I can tell who takes good notes and who believes and has confidence in themselves and people who don't believe in themselves. This reaction is a little bit different in its arrow pushing process than before, but it's a combination of hydride, hydrogen plus its electrons, plus the pi bond, going back and donating to the palladium metal or platinum metal center. We use palladium this semester. It's very strange. This alkene kind of floats down around and does this weird process. I'm going to draw another of that same little particle again, and what happens after this. After that first step, our alkene molecule is now bonded to the surface of gold. Then a second reaction step picks up the proton, gives the electrons back to the palladium, and the product is released from the surface. And the two hydrogens that have gone on have been inserted from the same side. Now, in this particular product, it's ethane. There's free rotation about this, so we can't see that these two come in from the same side. But if we take the example from the last slide, the one that you're required to know, if we actually take this flat alkene, this dimethylcyclohexene molecule, 1,2-dimethylcyclohexene, and add hydrogen to it, this molecule is flat, it floats in along the surface, there'll be hydrogen atoms sticking up, one of them will get plucked onto the molecule, there's another hydrogen floating, it plucks on the other one on the other side, and so this particular molecule, these two groups, the two hydrogens have added, they'll be coming up towards you. This is the key point that we have to remember, that these two groups go on with 100% cis stereochemistry, the result of syn addition. Syn addition comes from the fact that this molecule flattens out on the surface. One hydrogen comes in from the bottom, and then the second hydrogen comes in from the same bottom side. So both groups coming in from same side is called syn, means same side, gives cis stereochemistry. And cis is a concept or an idea that we think of as meaning same side. Okay. And we're going to start one or two more reactions today. We're going to do one more that's more in-depth and more detailed. This is one will require your mechanistic understanding. So we have enough time remaining to work on this. The final syn addition reaction is going to be called hydroboration, followed by oxidation, and this is going to contrast to some reactions we've done earlier. Let's recall two reactions. Draw what the outcome of this reaction is on paper, right? What the product of it is. If that makes you feel weird, use sulfuric acid. In this case, probably don't need a mechanism for this. Shouldn't need one. Just draw the product. Product we would expect from this is this alcohol. The alcohol comes in 50% from the top, 50% from the bottom. Today we learned about another method to do the same reaction. We could use mercury diacetate in water, followed by NaBH4. This will make the same exact alcohol product, same location, more substituted position. But using mercuric acetate, we don't have carbocation intermediates, so we don't have carbocation rearrangement. So there's some differences going on here. And let's contrast this. Same alkene. Step one. Let's use BH3. Step two. We're going to use potassium hydroxide and hydrogen peroxide. So these are the first general conditions. Normally all this stuff up here wouldn't even be here, the way we've been developing the notes. We've been developing the notes as alkene, some reagent, then product, then we draw out a specific alkene, we do the mechanism, we talk about details. But here I'm recalling these two ideas, and here, when we use borane and potassium hydroxide and hydrogen peroxide, the OH will go on the less substituted position. This is an example of anti-Markovnikov regiochemistry. That word I'll never utter on an exam, but for those of you using it in your dialogue or wanting to know, this is an example of an anti-Markovnikov product. Notice that the alcohol is inserted on the less substituted side. It's inserted on the less substituted carbon. I guess we could have flipped this around a little bit to make this a little bit more clear, but in essence, in the first two examples, this is where alcohol is going, the more substituted position. And of these two sides, this is the less substituted side. Well, technically I would have drawn this way so that it lines up with this, but it doesn't matter because it's definitely the same molecule as this one. Okay, so maybe this will be more clear in our notes if we're drawing it. Maybe we put the hydrogen here, but really doesn't matter. Point is, these two examples, the alcohol goes to the more substituted central secondary position. Last example, the alcohol is inserted on the less substituted primary position. There's not new rules at work here. It's just that these reagents follow the same rules and principles we've learned so far, but something switches at the last second where we can put OH in the outside. We're going to go through this process together right now. This will be the best use of our remaining 25 minutes together today.